So far we've talked about geometry and deformation of the truss. This is called kinematics. We've made no reference to forces. Now we consider equilibrium. So let's take the same truss example we've been talking about. And this time let's consider, again, we have node numbering, member numbering. And this time let's consider joint forces applied at degrees of freedom that are free. And for example, let's consider the equilibrium of joint number 3. And this is just like we did in statics in the method of joints. We take a free body diagram of the joints and consider all the forces acting at the joint. Notice that we're drawing all the member forces as though tension is positive. So if we do some of the forces in the x, we get this equation. If we do some of the forces in the y, we get this equation. Now we can do this for each joint and assemble all these equilibrium equations in the form of a matrix equation. So we have all the member forces are multiplied by a matrix, and then on the right hand side we have the joint loads. And now let's see how we fill up this matrix. So again, notice that we're going to label the columns of the matrix by the respective forces that that column is going to multiply, just for convenience. Okay, so let's write the sum of the forces in the x equation. That's what we get. Let's write the sum of the forces in the y equation for joint 3. That's what we get. Now, if we filled up all the equilibrium equations by doing all the joint equilibria, we get this matrix. Now, let's see if we can recognize this matrix. I suggest that you pause and look back at the previous video. We recognize that this matrix is simply the transpose of B, which is an awesome fact. So we can write equilibrium simply as B transpose F equals P. Now, so we have delta equals B times U, and we have B transpose times F equals P. We can assemble all of this information in the form of this picture. How do we connect delta and F? We know that F equals EA over L times delta. So we can assemble this for all the members, and we get this kind of an equation. And we call that matrix script E, which is 6 by 6. In this case, diagonal matrix. So each branch of this picture can be labeled kinematics, equilibrium, and this E matrix represents what we call constitutive equations. These are material properties. This picture is called Tonti diagram. Now, from this picture, we can deduce that to go from U to P, we can do B transpose E times P, and that's the stiffness matrix K. The interesting thing is, although we've developed this for the truss, all mechanics problems can be summarized in the form of this Tonti diagram. That's what makes this very useful. In assignment 2, we will develop Tonti diagrams for different mechanics problems. Also, all stiffness matrices look like B transpose E times B.